The history of C, Unix, and Linux, how they grew together, and why Linux still depends on C. Welcome to Gate and Kernel, where we explore how software connects to the hardware underneath. Most programmers learn C as a programming language and Unix as an operating system. But historically, the two are deeply connected. Unix helped shape C, and C helped Unix become portable enough to spread across the computing world. Decades later, Linux inherited much of the Unix model, and its kernel is still written primarily in C. To understand why, we need to go back to the beginning. 1. Before Unix, operating systems were closely tied to hardware. Early computers were very different from modern machines. There was little standardization, and software written for one computer often could not simply run on another. Operating systems were especially tied to the hardware because much of the system software was written in assembly language. Assembly gives programmers direct control over processor instructions and registers. That is useful for controlling hardware. But assembly has one major problem. It is specific to a processor architecture. Move an operating system to a different CPU, and large amounts of code may need to be rewritten. This was the environment in which Unix appeared. 2. Unix began at Bell Labs. Unix was developed at Bell Labs around the end of the 1960s and the beginning of the 1970s. Two of the most important early contributors were Ken Thompson and Dennis Ritchie. Unix was not originally written in C. C did not yet exist in its mature form. Early Unix was closely tied to assembly language and to the machines available at Bell Labs. One important machine was the PDP-7. Later, Unix moved to the PDP-11. That move exposed a serious problem. If the operating system remained mostly assembly language, supporting every new processor could require enormous amounts of rewriting. Unix needed a better systems programming language. 3. Before C came B. Before C, Ken Thompson developed a language called B. B was influenced by an earlier language called BCPL. So the historical path was roughly BCPL, then B, then C. B was smaller and easier to use than assembly. But the PDP-11 had features that B did not handle particularly well. Systems programmers needed better control over bytes, characters, memory addresses, machine words, and structured data. Dennis Ritchie began extending and redesigning the language. Those changes eventually produced C. At this point, the histories of C and Unix became closely connected. 4. C was built in a systems programming environment. C was not originally designed for websites, business applications, or graphical interfaces. It emerged while programmers were building an operating system. That strongly influenced the language. An operating system has to manage memory, processes, files, devices, buffers, interrupts, addresses, and hardware registers. So a systems language needs to stay close to the machine. But it also needs enough structure to manage large programs. C found an unusual middle ground. It provides functions, loops, conditions, structures, and other high-level programming features. But it also exposes memory through pointers. It allows direct bit manipulation. And it gives programmers significant control over how data is stored and accessed. C was much easier to manage than large amounts of assembly, while still remaining close enough to the hardware for operating system development. 5. Unix was rewritten in C. One of the most important events in software history happened in the early 1970s. Much of Unix was rewritten in C. At the time, this was a radical idea. Operating systems were expected to be written mainly in assembly because they needed direct control over the hardware. But the Unix developers showed that most of an operating system could be written in a higher level language. Some small, architecture-specific parts still required assembly. But the majority of the operating system could now be written in C. This changed the relationship between operating systems and computer hardware. 6. C made Unix portable. Portability may have been C's greatest contribution to Unix. Imagine an operating system containing a huge amount of processor-specific assembly code. Moving it to another CPU could require rewriting large sections of the system. But if most of the operating system is written in C, much of that code can remain unchanged. A C compiler can translate the same source code into instructions for different processors. Porting an operating system still requires architecture-specific work. Memory management, interrupt handling, boot code, context switching, and hardware initialization may be different. But the entire kernel no longer needs to be rewritten. That made Unix far more portable than many earlier operating systems. And portability helped Unix spread. 7. Unix helped C spread too. The relationship worked in both directions. C helped Unix become portable. Unix helped C become popular. As Unix spread through universities and research institutions, programmers using Unix encountered C. If you wanted to understand Unix source code, C was important. If you wanted to modify Unix, you needed C. And if you wanted to write software naturally within the Unix environment, C became an obvious language to learn. So a feedback loop developed. C made Unix portable. Unix spread. C spread with Unix. And more Unix software was written in C. An entire software ecosystem grew around the two. 8. The Unix interface also looks like C. The connection goes deeper than simply saying Unix was written in C. Many classic Unix programming interfaces were designed in a world dominated by C. A program can open a file, read data, write data, and close the file using simple system interfaces. Unix processes can be created with fork. Programs can be replaced with another executable using the exec family of system calls. These interfaces became fundamental parts of Unix programming. The operating system interface exposed to applications naturally fits the C programming model. That historical influence is still visible in modern Unix-like systems. 9. Linux arrived much later. Now move forward almost 20 years. In 1991, Linus Torvalds began developing the kernel that became Linux. Linux is not the original Unix kernel. It was developed independently. But Linux was strongly influenced by the Unix model. Linux adopted familiar Unix ideas such as processes, files, file descriptors, users, permissions, pipes, hierarchical file systems, command line tools, and system calls. That is why Linux belongs to the broader Unix-like family of operating systems. And when Torvalds began writing the Linux kernel, one programming language was an obvious choice: C. 10. Why was Linux written in C? By 1991, many programming languages already existed. So why C? Because kernel programming has unusual requirements. The kernel sits directly between applications and hardware. Applications make system calls. The kernel receives those requests and manages the CPU, memory, storage, devices, processes, networking, virtual memory, and interrupts. Many high-level languages intentionally hide machine-level details. Kernel developers often need the opposite. They need to see and control those details. C provides that control. 11. Kernels need direct memory control. Memory management is one of the clearest examples. Application programmers often obtain memory through libraries or language runtimes. The kernel cannot completely depend on those systems because the kernel helps create the environment in which those systems run. It must manage physical memory, virtual addresses, page tables, mappings, buffers, and kernel objects. C pointers fit naturally into this kind of work. A pointer can hold the address of a kernel data structure. Kernel code can follow pointers, calculate offsets, access memory directly, and organize complex structures with very little hidden machinery. That is exactly what low-level system software needs. 12. C lets the programmer control data representation. Hardware often expects information to have an exact format. A device register, for example, may use individual bits to represent states such as enable, interrupt, error, or ready. C provides bitwise operations that allow kernel code to manipulate those bits directly. C structures are also useful for representing complex operating system objects. Kernel developers can control fields, sizes, addresses, flags, and memory layouts with considerable precision. That matters because operating system code often communicates directly with hardware. At this level, the representation of data is not just an implementation detail. It can determine whether the hardware works correctly. 13. C has very little runtime machinery. Languages such as Python, Java, and C# normally depend on substantial runtime environments. Python usually depends on an interpreter. Java commonly depends on a virtual machine. These runtimes are extremely useful for application development. But the kernel faces a bootstrapping problem. Before an application runtime can operate, the operating system must already be running. The kernel cannot assume that a large runtime already exists underneath it. C requires comparatively little runtime support. C source code is compiled into native machine instructions that the processor can execute. That simplicity is extremely valuable at the lowest layers of software. 14. But Linux is not pure C. Saying Linux is written mainly in C does not mean every part of the kernel comes from C source code. Some operations are inherently architecture-specific. Processors may require special instructions for booting, entering privileged modes, switching contexts, handling interrupts, or controlling special registers. Those operations may require assembly language. So Linux is mainly C, with assembly used where direct processor-specific control is necessary. Linux supports many processor architectures, including x86, ARM, RISC-V, PowerPC, and others. Most kernel logic can remain common C code. Architecture-specific code handles the differences. This is essentially the same portability idea that made C so important to Unix decades earlier. 15. The compiler is the bridge. The compiler is what connects portable C source code to different processors. Suppose Linux contains a simple C operation that adds two values. On an x86 processor, the compiler generates appropriate x86 instructions. On ARM, it generates ARM instructions. On RISC-V, it generates RISC-V instructions. The kernel does not become automatically portable just because it uses C. Every architecture still needs specific support. But huge amounts of kernel logic can be shared. The compiler handles much of the translation from C into processor instructions. That is one of the reasons C remains so useful in operating system development. 16. Why not replace C with a modern language? Modern programming languages offer many features C does not. They may provide stronger type systems, automatic memory management, safer memory handling, better abstractions, and modern concurrency features. So why is C still so important to Linux? One reason is compatibility. The Linux kernel contains decades of mature C code. Another reason is tooling. Compilers, debuggers, analyzers, architectures, and kernel development practices have been built around C for decades. But there is also a deeper reason. C maps very naturally onto the way kernel programmers think. Addresses, values, structures, bits, registers, memory regions, and machine instructions are all visible. C is high-level enough to build enormous software systems. But it remains low-level enough to expose the machine. That combination is unusual. 17. Linux is beginning to use Rust too. C is no longer the only language used for Linux kernel development. Modern Linux has begun introducing Rust for certain kernel components. Rust is attractive because it can provide stronger memory safety guarantees while still compiling into native machine code. This is an important development. But it does not mean Linux has stopped depending on C. The enormous existing kernel codebase is still primarily C. Core subsystems, architecture support, memory management, scheduling, networking, drivers, and decades of infrastructure were built around C. Rust may increasingly complement C. But anyone who wants to understand Linux deeply will still encounter C everywhere. 18. C is a window into the operating system. This is why learning C can change the way you understand Linux. At first, pointers may seem like an awkward feature of the language. But once you study operating systems, they begin to make sense. The kernel constantly works with addresses. Study structures, and you begin to understand how the kernel represents processes, files, devices, and other objects. Study arrays and buffers, and input and output become easier to understand. Study bitwise operations, and hardware control becomes less mysterious. Study functions, the stack, and memory, and you move closer to understanding system calls and context switching. In the Unix world, C is more than just another programming language. It is part of the vocabulary used to describe how the system works. 19. From C to Unix to Linux. We can now see the historical path. Early operating systems depended heavily on assembly language. Unix began in that environment. B provided an early step toward a better systems language. Ritchie's work eventually produced C. Unix was then rewritten largely in C. That made Unix much more portable. Unix spread to more computers and more institutions. C spread with it. A large Unix programming culture developed around C. Years later, Linux inherited much of the Unix model. And the Linux kernel was again built primarily in C. C and Unix did not simply become popular at the same time. Their development was deeply connected. Unix helped create the environment in which C could prove itself. And C helped Unix escape from a single hardware architecture. Conclusion: C is old. Unix is old. But their age can make their influence easy to underestimate. C helped solve one of the fundamental problems of operating system development. How can programmers control a computer closely without writing an entire operating system in processor-specific assembly language? C provided a powerful answer. It offered low-level memory access, structured programming, efficient compilation, small runtime requirements, and direct control over hardware-oriented data. Unix demonstrated how powerful that combination could be. Once Unix was largely rewritten in C, the operating system became much more portable. Unix spread. C spread with it. Decades later, Linux inherited much of the Unix model and continued the same basic relationship between the operating system and C. Python can hide memory. Java can hide machine instructions. Modern frameworks can hide the operating system almost completely. C moves in the opposite direction. It exposes memory, addresses, pointers, bits, structures, and data layouts. And Linux operates precisely at the layer where those details matter. To understand C deeply is to move closer to the operating system. And to understand Linux deeply, sooner or later, you encounter C. C and Unix grew together. Linux inherited that legacy. And that relationship is still alive inside modern computers today. Thanks for watching Gate and Kernel. If you want to understand computing from programming languages all the way down to the operating system and hardware, subscribe to Gate and Kernel. I'll see you in the next lesson.